So in the reading assignment and in lectures, you've seen problems where you have some charge density rho, charge density, which produces some irrotational field F. So this F is the irrotational field produced by this charge density. Field produced. And using the divergence theorem, you were able to take this point form expression and get it to the integral expression, where on the left-hand side you have the outward flux of this vector field F through the closed surface S. And this circle you see denotes the closed surface. So this is outward flux of F through S. And on the right-hand side is the integral of the charge density, which gives you the total charge enclosed inside this surface. So this is total charge enclosed. For this tutorial, we'll be discussing problems with planar symmetry. They are the problems where charge distributions, instead of being functions of x, y, and z, are functions of just one of these variables, for example, y, and you could also have rho of x or rho of z, which would also give you planar symmetry. Example would be a problem like this one, where you have a slab and a sheet. Both of them extend infinitely in y and z direction. So the picture, when you move in z direction or when you move in x direction, doesn't change. But then in y direction, when you move, the picture changes. And then on this side, I'm showing you the cross-section. So this is cross-sectional view. One second. This is the cross-sectional view. And in those problems, the field produced would be in the y hat or negative y hat direction, and it would be a function of only the y coordinate. So both the charge density and the field only change in the y direction. Let's see an example. I'm showing you a sheet that extends infinitely in x and z direction. And this sheet is positively charged, this sheet is negatively charged, and now let's sketch the field that's produced. And I should mention this sheet is located at y equals 0. So the field would look something like this. It would diverge from the positive charge, and it's symmetric around the y-axis. To be more precisely, around the xz plane. And then the same situation here, but then the field converges on a negative charge. Now, I want to mention that the magnitude of F would be the same on the left-hand side and the right-hand side of this sheet. And you could also think that f of y, which is this y component of f, is an odd function. Why? Because it's positive on the right-hand side and it's negative on the left-hand side. And then here, same situation. Also, this f of y flips sign at y equals 0. So same scenario. Now, in the reading assignment, it's more common to use f like this, magnitude of f, but then I'll be using f of y. The reason I like using f of y is because I get to make it negative if I want to. If I don't know whether the charge is positive or negative, I could just keep a generic function here. Now let's talk about the field from multiple sheets. This isn't something that was discussed in the assignment, but I figured this discussion might help you understand it when you go back and read everything in detail. Okay, so here I'm showing you 3 sheets of charge, and each of these sheets has a different surface charge density. And you probably have figured that this is a cross-sectional view of this situation. And the goal is to sketch the field produced by these 3 sheets. And I'll do it by showing field from individual sheets first and then sketch the total field. Okay, so this sheet produces some field that is diverging from it, and it's symmetric like this. It goes like this, and then on the right hand side, it goes like this. And then here it also goes like this, the same way. Now, you see how I'm not changing the size of the arrows or the density of the arrows? I'm using the fact that the field from an infinite sheet doesn't diminish with distance. Now, I haven't shown it to you yet, but it's actually part of this tutorial, so just bear with me. Okay, this is for the red sheet. Now let's do the green sheet. This will produce field that converges on this sheet because the surface charge density is negative. So it would look something like this, like this, like this, like this, and like this, and like this, and like this. Okay, now the field from the blue sheet is going to be twice smaller than the field from the red sheet, but it's otherwise going to look similar. So it's also outwards from the sheet because the charge density is positive. So it's this way, this way, this way, and this way, this way, this way. Okay, and here it flips the direction. Okay, so now let's sketch the total field. Here you see you have long arrow to the left, which by the way is the opposite of what you have here. You have blue arrow to the left like this. It's a little bit shorter, but imagine we would need to add these fields together, and then we need to subtract this guy, which by the way cancels. These two things cancel, so you're actually just left with the blue field here. And you have the exact same situation here. The reason why is because for each of these sheets, the field on the left-hand side was the same as the field on the right-hand side, except it was a mirror reflection. So you see the field here, the total field, is going to be the same length as the blue arrow, but the most important thing I actually want to show you is that it is going to be symmetric outside of this charge distribution. So this is what I discuss. One second. What I discuss here. When we're outside the charge distribution, this field on the left and on the right has the same magnitude. And this is what you can use in different problems. And it's very important if, let's say, you're asked to find the field outside, you will need to make an assumption on how the field compares on the left side and on the right side. And the assumption you would be making is that the magnitude is the same on both sides. Okay, now this is not the case when you're between the sheets, because here the arrows flip direction. For example, when you go from here to here, this arrow, red arrow, flipped the direction, right? Now, when you compare this to going from here to here, it was the blue arrow that flipped the direction. So that's actually totally different. So the change in magnitude is going to be different here and here. And let's see it with the actual concrete field drawing. You see this arrow and this arrow superimposes, and this subtracts from it. So you actually end up with something that's this long. So something like this here. And then for this one, you see that red arrow and green arrow cancel. So you're actually left with just the blue arrow here. So you see how there is no actually, the symmetry is not the same. It doesn't look symmetric around this sheet anymore. So moral of the story, field outside of all the charge distributions is going to be symmetric with respect to, let's say, the y equals 0 plane. But then when you are sort of inside this charge distribution, the field is going to be much more complicated. So you can't any longer make an assumption that the field is symmetric around the YZ plane, for example. Now you can use all those results to draw a field from a slab, for example, which would be closer to what's discussed in the reading assignment. Let's say you have some, oh God, this looks horrible. You have your y-axis here, and then z and x. And you have your slab. And you have some arbitrary charge density. Let's say, and this charge density doesn't need to be symmetric with respect to y equals 0 plane. Let's say we have some positive charges here. Let's make them very positive. And let's make charges here a little bit negative. Then overall this slab is positive. So outside the field is going to sort of diverge from this slab. But what we learned just now is that it's going to be the same on both sides of the slab. So field outside has the same magnitude. But then the field inside doesn't need to wouldn't have necessarily the same magnitude, because this row of y can be quite complicated, like shown here. In this case, actually, let's say on z equals 0 axis, the field would go to the left. So you see, whenever, sorry, did I say y? Did I say z? It's actually y equals 0 axis. Okay, the field would go to the left on y equals 0 axis. And whenever you have a situation like this, it means that the field is not symmetric, right? Because it's to the left instead of to the right. In a symmetric case, there should be no difference between left and right. So then you see how outside the slab there is a symmetry, but then inside the slab this symmetry is not there. Now let's get back to the divergence theorem. In order to use the divergence theorem, you need to set up the Gaussian surface S. That's right here. And the best Gaussian surfaces for problems with planar symmetry are cuboids. And I'll show you why in a second. But the main reason is that you can simplify this integral on the left-hand side a lot and very easily if you choose this kind of Gaussian surfaces. So I'm showing you this red is the Gaussian surface with outward oriented normal vector. Let me show you the field that's generated by the slab. It would look something like this. This is the field. And then on the right side, let's say it goes to the right, but it doesn't matter too much. Now, what I want you to realize is that on this surface here that has a normal vector parallel to the negative y-axis to the negative y unit vector, and on this surface here, sy2, on these two surfaces, the vector field F is parallel to the normal vector. So it's either in the same or in the opposite direction. Now on every other surface, your normal vector is perpendicular to the vector field. And this is going to simplify the flux integral a lot. Let me show you the normal vector. So it goes here like this. It goes like this. And then let's say on this surface, it's going up. So when you take a dot product between this vector and this kind of vector, you are going to get 0. Let me actually show you F on this side. Okay, so these are perpendicular. What I also want you to realize is that everywhere on these two surfaces SY1 and everywhere on SY2, the magnitude of F remains constant. The reason why is because if you travel like this, so change your x coordinate, you see the exact same picture, so the magnitude of F should not change. And the same thing happens on SY2. Now let me show you the actual calculations. You see this flux integral on the left-hand side here. It can be broken down into 6 integrals here. You see how this sign that shows closed surface disappears on these integrations because these are not closed surfaces, they are open. And the main thing is that these integrals are all 0, these 4 integrals. The reason why is that this F and this vector ds have 0 dot product because they're perpendicular. So this would be SZ2, this top surface over here, and we just discussed how F and this n hat, which is in the same direction as ds, would be perpendicular. On these two surfaces, you have also a lot of simplifications. Let me remind you that the vector field in this kind of problems is equal to some function of y times the unit vector y hat. This is what I've plugged in here for F. And there is one more thing. You see how I put 1 here? So this is the y coordinate of SY1, because you know that we need to evaluate this vector field on the surface in order to get this integral. And then the same thing here. We need to evaluate the field on the surface. Okay. Now, this is a constant, so it comes out of the integral. And the same thing happens here. It comes out of the integral. There is one more thing that's happening, is that this dot product is equal to negative ds, where this is a scalar number. Now let me explain why. Y hat dotted with ds, with the vector ds, this would be for the surface SY1, is equal to the magnitude of y hat, which is 1, times the magnitude of ds, which is this ds, times the cosine of the angle between the two. Now, on SY1, n hat is in the negative y direction, and y hat is, obviously in the positive y direction. So the angle between the two is 180 degrees, and cosine of 180 is negative 1. So times negative 1. That's why it's negative ds. On SY2, you have a similar situation. You have y hat dotted with ds equals to magnitude of this times cosine of the angle between the two, but these two vectors are parallel because n hat is in the direction of y hat. So you'll get times 1. That's why this is ds. So on the next line, what I did is I took out these fy2 and fy1, and I also took these signs, minus here and plus here, out of the integral. Now, you see that this guy is the integral giving you the surface area of sy1, which is what I wrote here. This is the surface area. And the same thing here, sy2. I could also have used a because it's planar. And the main message I want to get across is that all of these simplifications were only possible because we chose the Gaussian surface that respects the symmetry of the problem. For example, this simplification, you see how I crossed out a whole bunch of integrals, is only possible because these two vectors are perpendicular. This simplification also used the fact that the vectors are either parallel or they go in the opposite direction, so I guess also parallel. This part used the fact that magnitude of f doesn't change on each of these surfaces. Now, if you choose a surface that doesn't respect the symmetry of the problem, this integration cannot be simplified like this. So this is it for the left-hand side. For the right-hand side, everything is dependent on what the row is. So I'm just going to give you some examples of what this row could be, and the rest is going to be part of examples. So row of y can describe, for example, a continuously distributed charge over the volume. For example, uniform charge density inside a slab, that's one example. Another example would be rho that is some function like this of y. Rho is measured in coulombs per meter cube. And this slab, let's say, is given to be going from some left y value to some right y value. So this would be y equals yl, and this would be y equals yr, and this would be your slab that has rho as a function of y. You could also have charges of the 0 thickness. Those would have expressions like these ones. Its rho is measured in coulombs per meter cubed again, and the charge density is equal to some surface charge density measured in coulombs per meter squared times delta of y minus the y position of the sheet. Let me draw this. This would be a sheet of charge. It would sort of be shifted to the coordinate to the coordinate y equals y sheet. Now let's discuss the portion of assignment 5, section 3.1 that deals with finding field from a slab. The problem statement is like this. You have rho of y that equals to 1 plus y from some left side to some right side. You see this d is the thickness of the slab. So you have d, thickness of the slab. Your rho of y is given by 1 plus y. And your goal is to find f everywhere. The first step in the solution is to find the field outside the slab, and then using this information, the second step will be to find the field inside the slab. For step 1, first let's set up a Gaussian surface. It's going to go from it's going to be a cuboid that goes from x equals x1 to some x2, so totally generic. then Z will also be general from Z1 to Z2. Now for Y, I'm going to make it so that it's symmetric. So I'll select the Gaussian surface from negative Y2 to Y2, where Y2 is some positive number. So your Gaussian surface is going to look something like this. This would be the SY2, and on this side we have S negative Y2. Let's also sketch the field. The field is going to be like this here and like this here. This is the field. Let's evaluate the left-hand side of the divergence theorem. Again, integral over all surfaces that are like this and like this cancel. Sorry, not cancel, they are 0. The only integrals that survive are S negative Y2 and S Y2, the two integrals here. Now, on the SY2, actually, I'm going to draw it in red. On SY2, we have the normal vector that is pointing in this direction. So we could think n hat is this way. We could also think ds, which is a vector, is this way. And the field is, well, let's assume it's to the right. We actually know it's to the right because this is overall positive. But like if you integrate it, but that's okay. We don't have to assume it's to the right. But let's say it's something like this. For this surface, what we have is normal vector going in the opposite direction, but the field is also going to go in the opposite direction. This is the reason I said it doesn't matter if it's to the left or to the right. What's important is that it's in opposite direction from what it is here. So you see how both n hat is flipped and f is flipped. Let me label everything so you have a reference for your notes. This is SY1. Sorry, S negative Y2. Okay. The reason I said it is because since both n hat and f flip, it means that their dot product has the same sign for both integrals, and we know that the magnitude will also be the same. And the two surface integrals, the only thing that could differ is the sign, because magnitude of f is the same on both sides. But we just determined that the sign is actually the same, so these two integrals are the same, which is why here I wrote that this is just 2 times this integral. Okay, next step is to evaluate what it is. So we have 2, then this integral. Here again I plugged in f equals to f of y times y hat and plugged in y2. Then I took this guy out of the integral. Got to here. I also realized that y hat dotted with ds for this sy2 is equal to ds because y hat is in this direction and ds is in the same direction, so the dot product is positive. So we have this equal to ds, which is a scalar. This is what I wrote here. Then this integration gives you the surface area of this surface, right? This is where I got this line. This sy2 is the surface area of this guy. Now let's move on to the right-hand side of the divergence theorem. Here we have the integration of rho. our z integration just goes from basically just goes from the lower to the upper bound of the cuboid. Same goes for x1, sorry, for x. Now for y, it's actually really important what you put here right now. So because I put 1 plus y in the integrand, I actually need to put, instead of negative y2 here, I need to put negative d over 2. And it's really important that you get this step right. And upper bound is d over 2. So I'm integrating, instead of from here to here, I'm integrating from here to here. The reason why is this. When you set up this integral, this v here, which I totally forgot to label, this v here, sure, it goes from y1 to y2 or negative y2 to y2, but then if you want to put negative y2 here and y2 here, you can do that, but then in the integrand, you need to be aware of the fact that the density is non-zero only from negative d over 2 to d over 2. Let me actually label it. Negative d over 2 to d over 2. So then you would write something like 1 plus y for y between negative d over 2 to d over 2, and then 0 otherwise. And then you would continue with setting up the integral. Then the next step is going to simplify to this, which is why I just skipped this step and wrote this directly, but it's really important that I put the actual bounds of the charge instead of the bounds of the Gaussian surface in here. Okay, then we need to evaluate this integral. Integration over z is just going to give us z2 minus z1. Same is going to happen for the integration over x, x2 minus x1. Now for integration over y, you see how y is an odd function, right? And our integration bounds are symmetric. It's from negative number to the positive number, which is like the same in magnitude. That's why this integration gives you 0. So integrates to 0. So you're left with 1, and this integration as a result is just going to give you d over 2 minus negative d over 2, which is d. Now this part times this part is just the surface area of SY2, which is what I wrote here. Now let's equate the left-hand side and the right-hand side of the divergence theorem. And sorry, I didn't put it here. Okay, and then solve for unknowns. But okay, left-hand side is this, and the right-hand side is this. So then I equate the two things, and then I would solve for Fy2. This is going to be equal, after I cancel Sy2, going to be d over 2. What does it mean? So I found that on this surface, y component of f is equal to d over 2. On this side, it's going to be negative of that. So we know that for y being on the left of the slab, we have f equals negative d over 2 y hat, and on the right of the slab, we have d over 2 y hat. Now I want to mention that I've deviated from the reading assignment just a little bit for this part. In the reading assignment, in order to find the field outside, you would break up this row into even and odd parts, and then odd part was shown to produce no field outside, so the field would only be inside. Row even would produce symmetric field everywhere, which would essentially give you symmetric field outside. But then to solve the problem, in the reading assignment, superposition was used, so you would calculate field from odd and even parts and then find the field and add it up in the end. In this tutorial, since I argued that the field is symmetric outside, even if row is not necessarily symmetric, I just ended up solving the problem directly. Both approaches are valid, so and the answer ends up the same, so you can use whichever one you like better. Now let's find the field inside of the slab. To do this, we would use the field that we just found that's outside the slab and set up the Gaussian surface in such a way that we can use this information. So let's set up Gaussian surface with the left side aligning with the left edge of the slab. So something like this. So our y for this cuboid, which is the Gaussian surface, is going to go from negative d over 2. So this would be s negative d over 2 up to some arbitrary y2, which is inside of the slab. So this would be sy2. This way, here's what we have for the integral, for the flux integral. Again, we are breaking the integral into 6 parts, but only 2 of them survive. On each of those parts, for this left one, I plugged in what f actually is on that surface. It's, the y component of f at y equals d negative d over 2. F is in the y hat direction. For this guy, I did the exact same thing, plugged in f of y2 times y hat. Then I used the fact that on this surface, we have ds going in the negative y direction. So this means that this dot product is equal to negative ds, where ds is a scalar. For this surface, this one, we have the differential surface element that goes to the right. So when you dot product it with y hat, you get positive ds. For this integral, this f of y2 comes out of the integral because it's a constant. So we're left with f of y2, you see this here, times the surface area of this surface. Now you see I removed the subscript because this surface area and this surface area, of this guy are the same, so I don't need to distinguish between the two. This is for this term. Now, for this term, I have a negative. This is how it ended up here. This is a constant, so it comes out of the integral. And I'm left with the surface area of this surface, so here I put sy. Now let's use the information we got from the previous part. We need f at negative d over 2. So the y component of f at d equals negative d over, at y equals negative d over 2. You see, this is the field on the left side of the slab, and this is the y component. So we put negative d over 2 for the y component. So this guy would be equal to negative d over 2. This is why this negative cancels, and you're left with d over 2, and then you have sy plus this term. This didn't change. For the right-hand side, we have the same integral. Sorry, I forgot to label. The same integral of charge density. everything looks the same as before. We're integrating what the charge density is for the same x bounds and the same z bounds. For y, we have integration from negative d over 2 to y2. Remember the issue with having to only integrate over the actual charge? In this case, we don't need to worry about it because, well, our Gaussian surface is entirely filled with a portion of the charged slab. There is no empty space there. So this integrating from here to here will give us the correct charge. Okay, now let's proceed with integration. Z integral will give us z2 minus z1. X integral will give us x2 minus x1. Y integral will give us, for this one, it's y plus, this gives y squared over 2. Bounds are negative d over 2 to y2. Then I use the fact that this times this gives me the surface area of the surface, Sy, and then here we have this same surface. Okay, and then I evaluated what this is. This is the only thing that's left. This gives us, well, y2 minus this one. So this is what I wrote here. And then plus this guy at y2, which is this part, minus this same thing at negative d over 2, which is this part. And then again, we have the surface area times y2. Then this becomes a plus. And then we have, let me actually use a different color so I can show you. Okay, so this cancels, becomes a plus. This plus y2 squared over 2, and then this minus is here. This minus disappears. This becomes a 4 because of the square, so you get 8, which is right here. This is how I got this part. Now let's solve for f of y2 by equating left-hand side and right-hand side of the divergence theorem. So the left-hand side, which is the flux integral, is this, which I copied over here. And the right side is this, which I copied from here. By the way, in the final version of the notes, I'm going to remove this subscript. Okay, so, right. So I've equated the two things. Let's solve for f of y2. So you have, I don't like this color. You have f of y2 equal to s of y cancels. And then we get y2 plus d over 2. D over 2 actually cancels as well. So we get y2 plus y2 squared over 2 minus d squared over 8. So this is it for f of y2. Now we figured out that, okay, we have this slab, and on this surface, our field has a y component given by whatever the location of the surface plus location of the surface squared over 2 minus d over 8 squared. So for an arbitrary location, arbitrary would be just y, we would have a y component given by this. So we can get f equal to y plus y squared over 2 minus d squared over 8. And the direction is y hat. We found the field outside, we found the field inside, and this is all there is to this problem. Now let's do problem 1 from section 5 of reading assignment 5. you are given surface charge density in coulombs per meter squared, shown right here, and you're asked to find the field everywhere. The first step, as usual, is the Gaussian surface. This would be a cuboid. We want to, because the field is symmetric, let's set up the surface in a symmetric kind of way. So field on the right is the same as the field on the left, except flipped. So let's actually set up our Gaussian surface so that this surface, SY2, is at the same distance from the sheet as this surface. So this would be S located at negative y2. So this would be negative y2, and this would be y2, where y2 is some positive number. Okay, let's simplify the left-hand side of the divergence theorem, which would be the flux. It's equal to the integral to the flux through the left surface plus the flux through the right surface. Now I claim that this is equal to 2 of this integral. So I basically say that these two integrals are the same. Here's why. For this integral on the right-hand side, you have ds going this way and f is going this way, right? For this integral, ds is going in the opposite way and f is going in the opposite way. And by the way, magnitude of f in these two integrals is the same because of the symmetry and because of we set up a symmetric Gaussian surface. So you see that the signs are the same and everything else is also the same. So then you end up with 2 times this integral. Again, I plug in this expression for f, and then I realize that y hat dotted with ds for this surface is going to be equal to ds because y hat and vector ds is in the same direction. So then what I'm left with, once I take this guy out, I'm left with the surface area of this surface on the right-hand side. Now let's work with the left-hand side. For the left-hand side, we have the integral of charge density for x going from x1 to x2, z going from z1 to z2, y is going from negative y2 to y2. Remember, this is how we chose our Gaussian surface, negative y2 to y2. Now I separated this integral. Sigma comes out of the integral. Then we have integral x1 to x2 of dx, z1 to z2 for dz, and for y is going from negative y2 to y2. Now this integration is just going to give us the surface area of the basically this chunk that's cut out by this surface, which is equal to sy2. So then we have sy2, or we can call it sy. For this part, we have a delta function that peaks at 0, right? And this interval captures the peak entirely, so you end up with this integral being equal to 1. So then this is equal to sigma times sy2 times 1. So this is the right-hand side. Now, there is a second way to evaluate the right-hand side integral is by using the surface charge density directly. Surface charge density physically means amount of charge per unit surface area. The amount of surface area that's cut out by this Gaussian surface is this much, right? So basically inside the Gaussian surface, this black area is the one that's is the charge that's captured, and its surface area is equal to SY2. So then you end up with sigma times SY2. Again, let's equate the left-hand sides and the right-hand sides to solve for the field. So here I copied the left-hand side, which was the flux. This was the charge enclosed. This gives us f of y2 equal to sigma. Actually, let me cancel this first. This is equal to sigma over 2. So then on the right-hand side from the sheet, the field is going to be sigma over 2 times y hat. And on the left-hand side, it's negative sigma over 2 y hat. And the units are coulombs per meter squared. Now I promised to you, that I will explain why the field doesn't decay. So actually, you see, this is just a constant, right? It doesn't depend on y. So when you move away from the sheet, you end up with the same field. Now let's do problem 3 from section 5 of assignment 5. In this problem, you're given two sheets. Each of those sheets has surface charge density sigma, and you're asked to find the field everywhere. Now, I want you to realize that this problem is no longer symmetric because the charge density is not a function of just y, basically, if you change z coordinate, the picture changes. So we don't have the same kind of symmetry we had before. So to solve this problem, what we'll use is superposition. We will find the field from the sheet that's parallel to the xz plane, which is the sheet that's green. And then we will add it to the field produced by the sheet, which I will draw in purple, which I'll call xy. This is what I wrote here. Total field is equal to fxz, which is the green one, and add it to fxy. Fxz for y that's less than 0, so on the left side of the sheet, is equal to a negative number, so has negative y component. So it's negative sigma over 2 times y hat, because it goes like this. On the right-hand side, it goes to the right, so we get sigma over 2 times y hat. For field xy, we have the following. We have the field going up for z that's positive and down for z that's negative. So for negative z, we have negative sigma over 2 z hat. For z positive, we have plus sigma over 2 z hat. Now we want to add these two fields together, so we end up with 4 different regions. You see it's both y and z negative, then y flips the sign, and then the same thing for z. Let's fill in all the fields. So for y that's negative, we use this value. So we have negative sigma over 2 y hat. Here we have negative sigma over 2 y hat. For positive y, we get plus sigma over 2 y hat plus sigma over 2 y hat. For z that's negative, we get this. So negative sigma over 2z hat, negative sigma over 2z hat, and here we get plus sigma over 2z hat, plus sigma over 2z hat. This was it. We actually found the field everywhere. Now let's sketch it. I'm going to actually sketch the green field from xz first, and then I will sketch the purple field, and then I will add the two together and see what happens. This is the green field. This is the purple field. So here's what we have in total. On this side, we have the field going sort of like this, and then I guess it's like this here, here. So this is the field pattern on this side. For this side, we have this. For this side, we have this. And for this side, we have this. Now I want you to realize that this field doesn't have the planar symmetry. So you really shouldn't be solving this problem directly. And let me justify why a little bit. You see, if you are evaluating the left-hand side of the divergence theorem, when you set up your Gaussian surface, you see how your field is no longer perpendicular or parallel to the to each of these surfaces. So that's a big complication, and it's probably tricky or maybe even impossible to take it into account properly. Maybe for this problem it could be possible, but it's just way too tricky. It's not worth doing directly. So let me write this formally. So your ds vector, neither parallel nor perpendicular to the field. Also, remember how we had this trick when we wrote f like this, and then we took this y component and then we took it out of the integral because it was a constant on all the surfaces of interest. Now we can't really do that because, well, first of all, your field has two components. It doesn't just have y component. Also, it's, for example, for this surface, you have the y component flip sign. So actually, you need to consider this surface with a lot of care. So it gets too complicated. And really, the simplest and the best solution to this is to use superposition.